Good morning and good afternoon, everybody that is connected to Cascadia's Windows webinar for today. I'll just spend a couple of minutes introducing myself, Cascadia, and a couple of administrative items to make the webinar go smoothly. Now's a good time if you have to do one last coffee cup warm up or something like that. We'll get into the nuts and bolts of what we're going to spend our learning session on in just a minute. So my name is Michael Bousfield. I'm the Technical Director at Cascadia Windows and Doors. Today's learning session is going to focus on combustible components used in non-combustible construction. And we're going to be talking about the building enclosure of that non-combustible construction. We're going to be focused there on combustible components in the building enclosure. Just to cover a few items, again, to make this webinar go smoothly. I hope everyone's had a okay time connecting here and no technical trouble. If you run into a technical problem with the software midstream and you want to ask a question or telephone somebody for technical support, that exists. It's a telephone number in the email that you received from the webinar system, which contained the join webinar link. So if you need that technical support, that telephone number is there. For all of you interested in receiving the continuing education credits, the certificates for AIA or AIBC or CPD credits for BC Builders, you will receive an email following this webinar about an hour after we finish. In that email, there will be a link for you to download your certificate. And if you have any questions or if there's any problem doing that, just hit reply to the email. It will actually come directly to me and we'll help you out. During this webinar, please ask questions. Questions can be asked by typing them in to the webinar software's question box. So on your control panel there, I'll receive your questions. I may not be able to address your questions the moment you ask them, but don't worry. Even if I save them or some of them to the end of the presentation when there will be a question period as well, I will be able to answer all of the questions during the webinar, even if I leave them to the end. Finally, if you have connected to this with audio and you have dialed in to a long distance number to hear that audio with your telephone, depending on your long distance plan, if you're paying for that long distance, then we'd recommend for your economic good to choose something else like connecting through your computer. And with that, let's get going. Now, I'm going to turn off my video feed to maximize the size of the slide and to help anybody who has a lower bandwidth connection get the most out of the webinar. I'll come back on at the end in the question period. So there we go. Okay, so in our learning session today, we're going to first look at what stuff is combustible and in the building enclosure. And there's more of it today than there ever has been, but that doesn't mean that we're compromising anything. We're going to look at why that is. Why is there combustible stuff in non-combustible buildings, building enclosures? We're going to look at combustible cladding supports for the opaque walls. We're going to look at combustible window framing for the fenestration area. We're going to be focusing on why these things exist and how safety is assured and maintained throughout, including what studies have been done. We're going to wrap up by looking at interestingly enough, in the window industry, an industry research project that was conducted with Enercan and actually triggered a building code change for the upcoming National Building Code 2020 in Canada that is going to further expand the safe use of what I've referred to as combustible windows and catch us up to the States and Europe and pretty much everywhere else. So that is all to come. First, combustible a quick intro to Cascadia before we get into that. So Cascadia Windows, as you've probably already guessed, is a manufacturer of fiberglass windows and doors and a cladding support system known as the Cascadia Clip. And we've focused on fiberglass for our product line for building enclosures products because fiberglass gives us the opportunity to work with a very structurally predictable material, but it also has advantages for thermal conductivity. Very, very low thermal conductivity equals low rate of heat transfer, which is ideal if you're trying to preserve the heat to keep it on one side of an insulated assembly and prevent the loss. So if you're trying to make a building enclosure assembly efficient regarding its insulative characteristics, the use of low conductivity materials is key to making that happen. Now, from that focus on energy efficient materials, we've come to articulate that as a company, our purpose is to provide simple and cost-effective solutions to ever more stringent energy code requirements. And you can look almost anywhere in North America and see local and regional examples of ever more stringent energy code requirements. And I think for our eventual good, that is a good thing. So with our look into the building enclosure and these ever more energy efficient components, we're going to look at why is there combustible stuff in there? We're going to look at composites, and we're going to look at energy codes and conservation. So we need to look at sort of why are we doing this before we look at how are we doing it safely. So we've built building enclosure assemblies with combination of combustible and non-combustible stuff for a very, very long time. And here's a picture of an exterior insulated wall on a non-combustible building. It has simple metal Z-girts, which are going to be the cladding supports. It has mineral wool insulation. Neither of those two materials are combustible, but there's a layer of membrane. It's a waterproof membrane. It serves a function of air barrier and vapor barrier as well in this assembly, and it is combustible. It is combustible because that product at that location is necessary for performance. It does a good job. It actually does not compromise safety. So it's fine to use it, and these walls perform well. So as an extension of that, why is there more stuff? What else needs to perform better? Well, as energy codes require more and more performance out of the same assemblies we've built, there's going to be a more of an introduction of composites, plastics, fiberglass, rubber, let's just collectively say composites, non-metal stuff in our non-combustible building assemblies. And they're there, and these changes are occurring because they trigger much, much greater insulative efficiency from these assemblies, these walls and these windows, and they're present to reduce the heat flow that would otherwise occur if those components were the more traditional metal sizes and shapes and styles. So just like the membrane was used for the necessary performance that we demand from it, and it happens to only be possible to provide a combustible component there, so too will composites become introduced. And this photograph features a fiberglass thermal spacer separating metal cladding supports only on the outside of the insulation layer from the steel framed wall on the inside of the insulation layer, but it's fiberglass that's passing through. So that's why there's an emergence of composites. Composites are going to play a huge role in more energy conserving buildings. Quick look at why do we have to push our building performance and building enclosure performance specifically up a notch or two. I'll get to an audience participation slide here in just a second. I wanted to do a quick nod to our possibility to do some good at mitigating climate change in the practice of our profession here in the construction industry. First, acknowledging that if we were to divide the carbon emissions from society into three really coarse categories, industry and buildings and transportation, buildings are the biggest one. About 44 to 45% of all North American emissions come from either operating buildings or constructing them. So we have an opportunity, if we can do some good for mitigating climate change, we are actually aiming our efforts at the biggest piece of the problem. I really hope that we're successful in those efforts. So focusing on our industry, why are our buildings consuming so much energy? So here's my audience participation slide to keep us focused on the building enclosure. I'm going to show pictures of three buildings, one after another, and if you've attended one of our earlier presentations about Windows, you've probably seen this question before. That's okay. I'm going to give you some comments about each of these buildings in turn. Between each, I'm going to activate a multiple choice question to come onto the screen, and you're going to be able to guess, and I want you to guess what is the overall thermal resistance, the overall R value of that building enclosure, incorporating walls and windows and all that you can see in the pictures. Okay, so here are the clues for the building number one. This building is about 85 years old in Vancouver, British Columbia, Canada. It has a brick veneer. In board of that brick veneer, it has a steel framed wall, and there is insulation, some insulation inside that steel framed wall. There are punched windows, lots of windows, but it doesn't account for a massive amount of the area, and there's some insulation in the roofs as well. So here's our first audience participation slide. Please choose your best guess of R value for that whole building. And I'm going to share the results in just a second. And at the end of the three, I'm going to provide the actual answers. Thank you guys very much for participating. Just a couple more seconds to click on your guess. Okay. So here's everybody's guesses. And I see a couple of people might have played this game before, but here's building number two. So this building is just over 30 years old. It's in also Metro Vancouver, British Columbia. It is a residential building consisting of half mass concrete. The mass concrete has a steel frame wall inboard of it with insulation in that steel stud cavity. The other half of the exterior is double glazed windows with not thermally broken aluminum frames. So here's round two. These are the same choices as the first time you saw this multiple choice slide. Just a couple more seconds. And there's everyone's guesses. And then finally, building number three. So building number three is a more modern building and a lot more glass. It has double glazing in that thermally broken aluminum window wall. It has spandrel bypass in front of all the slabs with some insulation in that bypass area. It has some concrete slabs fully exposed at those small stacks of balconies. Okay, so taking that in its entirety, what do you guess? And we're going to close that and share those results. And now I'm going to thank you everyone for participating. So the results are that the second choice was right in all cases. All of these three buildings have somewhere between R2 to R3.5 for their whole building enclosure combined. And the unfortunate part about this really is that if you look from left to the right, we're actually starting at the higher end of that range and moving to the lower end of that range. So things are getting worse as time goes on, mostly because regulation hasn't stepped in and demanded more. To give everybody a non-construction industry example of this, somewhere in between this range is the R value of a good fur coat. So take that for what it's worth, but it doesn't appear that our industry has truly been setting buildings up to be all they can be from a thermal perspective, despite the passage of time. But energy codes are coming in more and more in the last, not even the last 10 years, really effective energy codes have only started to come into play in less than the last 5 years in most locations of North America. For energy codes to work, the methods need to be comprehensive as they're starting to be, but those methods still need to rely on components. So we need components to deliver better performance from the assemblies we'll inevitably use. And what is the key thing about those components? The key thing about the components is whatever is providing the insulative layer, we need to get the highly conductive parts and pieces out of that insulative layer to let that insulation do its job. When you're talking about a wall, therefore, cladding attachment matters the most. Doesn't matter about insulation type, really. It doesn't matter about insulation thickness very much. What matters is how efficiently we use what insulation we have. And if you look at this slide, 12 inches of insulation on the left, one single continuous metal Z-girt is passing through that layer. On the right, these intermittent fiberglass spacers are the only thing thermally bridging the insulation layer. This is meaningfully better on the right-hand side in terms of whole wall R value. It's not slightly better, just to make the slide truthful. It's meaningfully better. It would probably remain truthful even if that assembly on the right-hand side was only 2 inches thick. Now, so that's walls. In windows, so in walls, cladding attachment matters the most because we have the opportunity to fit those composite materials where they need to go. In windows, window frame materials matter the most. And we can see that when we compare typical thermally broken aluminum frames to any sort of composite frame where that low conductivity frame material is the entire frame rather than just a small break in the middle of it. In this comparison that's on the slide here using industry average values for both thermally broken aluminum and fiberglass double glazed windows, we can see that we have about an 80 to 90% improvement just by changing the frame type. We've stuck with decent double glazed units in both. We've stuck with NFRC certified sizes in both. So we've held other things equal. We've just changed the frame type. So the thermal bridging in the case of the lower R value was caused by the frame, not by the size, the shape, or the glass in the window, but it was the frame material itself. So materials matter. And we're going to address both walls and windows, but first we have to address something bigger and more important than the detail about what material goes where in either of these assemblies. And that bigger, more important issue is fire safety. Big picture, we are trying to and must avoid this. And this photograph comes from the unfortunate tragedy of the Grenfell Tower in London. We have to ensure that we're designing our assemblies as energy efficient as they might be to prevent this. We have to maintain fire safety. Now, the good news is we can. So we're going to look at a little bit right now at some building code objectives, and that will inform the rest of the presentation on how those concepts of fire safety and performance in non-combustible construction are preserved. So the following few slides were generously provided by LMDG building code consultants in a co-presentation that we did with them a while back. So even though some of the code, most of the code references here are related to Canadian building codes, it's equally useful for an American audience because even though the code reference themselves may be different, the concepts and the objectives of these things we're going to review are exactly the same. So we'll hit relevance here for both audiences. In our building codes, when we look at combustible characteristics, when a non-combustible building is going to have combustible things in it, the materials either need to be, well, not combustible, or if they're combustible, they're permitted if they are a limited combustible component, which can be defined from a bench scale test, or the combustible components could be permitted because they comply with an exemption. The idea of either permitting through this test or permitting through an exemption is the objective of controlling fuel or controlling the combustion process itself. So the functional statements about controlling fuel and or the combustion process is to limit the severity and the effects of a fire or an explosion. And this actually helps us clarify what constitutes non-combustible construction. It's to limit the probability that the construction materials themselves will contribute to the growth and or the spread of fire, which could then lead to harm to people or damage to the building. So how do you limit that severity? You limit the severity by either, number one, preventing ignition in the first place, or number two, if you cannot, then you manage the fire spread to limit its possibility to spread. And we know we need to have some combustible materials in buildings, anything from electrical wire shielding to tape on drywall to fiberglass spacers in wall assemblies to thermal breaks in windows. We need combustible components, and we are permitted to use them because so many of them can be safely used. But how does the building code address and categorize how something could be safely used? Well, they're looking to control fuel. permit a certain amount of combustible materials on the basis that they are deemed to insignificantly contribute to fire growth or spread if they're used. Now, there's a lot of different categories of materials, and so we're only going to focus on two. We're going to focus on combustible glazing, which is essentially combustible fenestration framing, and we're going to focus on combustible cladding and cladding support components. So first one, the combustible cladding. Now, when we're just talking about cladding generally, in Canada, there's a large-scale test called the S134 test, and in America, the Nfpa285 test is the closest test to it. It's a multi-story assembly, and it is actually used for permitting a combustible cladding system to cover a whole building's wall. Well, there's some justification for that test, and I'll explain it by reviewing the spatial separation requirements between your building, which may be on fire and you're responsible for either as a designer or an owner, and an adjacent building where the code doesn't want fire spreading through a neighborhood. And so the idea is that the closer your building is to its property line, the more it could theoretically risk an adjacent building or a building on an adjacent property. So the closer you are to that line, the more stringent the requirements are for the construction of that face of your building. If you're right on the property line, you need to construct a firewall. Non-combustible cladding, wall has to have a rating, no unprotected openings like regular windows. Now, if you're a short step away from that property line, you don't have to have a fire rated assembly per se. You have to have non-combustible cladding. You're permitted perhaps 10% unprotected openings after a couple of steps away, and then after you get a certain distance away, you can have unprotected openings. So the interesting one is right here. You can use cladding from this point back if that cladding is combustible but meets the requirements of a large-scale test. And here's an explanation of the test, very similar to Nfpa285 test for people who are more familiar with the American version. The idea of these large-scale tests, whether they're the S134 in Canada or the Nfpa285 in America, it is to set an uncontrolled fire or simulate an uncontrolled fire in a lower room, which is going to burst out of a window in that wall, and the flame front is going to travel up the wall. Of course, if that wall is clad with a combustible cladding material, that fire is going to have a much easier job of spreading. And the test, therefore, is determining how much heat does that combustible cladding radiate away from it? Could it catch an adjacent building on fire because so much heat is radiating? The other thing is, how high do the flames climb? Are we risking the fire busting back into the building a couple of floors up and skipping floors and accelerating its way all the way up the building? So the way that the Canadian version of this test occurs, and it's basically a 3-story tall test, is that there's a fire chamber and a flame coming out the front of it, and there's a radiant heat flux gauge, and there's a visual limit at 5 meters or 16.5 feet. And this limit is the limit for flame spread. So the flames can spread somewhat, but not past that point during the test. So during this 1-hour test, the fire is started, and the fire gets so large that the immediate surroundings above the window, if they're not non-combustible materials like concrete and steel, they'll just get turned to ash. But that's okay, that's expected in the test. And then the test proceeds, and then this little example here, this final slide would indicate a failure because it's illustrating flames climbing above that limit. So this would have been caused by the fire from the chamber catching the combustible cladding on fire and the fire spreading too much. It would not meet the requirements of the test. So a lot of common products are successful at passing this test, and ACM panels are one of the most common products. So if you wanted to visualize a cladding material that is often subjected to these tests, just imagine ACM materials, phenolic panels, things like that. If we take a more detailed look at the components behind them, because this all started by looking at the introduction of more composite materials into building enclosures because of needs for greater energy efficiency. So we're going to look at that component in more detail. That's a more recent addition in the big picture. Why a combustible spacer? Well, like I've said before, compared to metal, composites, fiberglass, plastic, rubber, whatever it is, offers an excellent reduction in the thermal bridging that is naturally going to occur in metal. So if there's a variety of these types of products, actually, these cladding support brackets and spacers on the market now. This one on the left, this fiberglass thermal spacer, this is Cascadia's product. It was one of the first in the industry. There's probably now more than a dozen mainstream options, and they mostly differ between mostly metal components or mostly composite components. So I'm actually going to show this comparison twice. I'm going to use this spacer as a baseline for the comparison. So compared to mostly metal systems have adjustability, just like this spacer has adjustability, but this common design of what is generically showed here as a bracket and rail metal cladding support system is that the metal rails or the metal supports are usually adjusted into the insulation layer in order to provide adjustability. That reduces the energy efficiency of that portion of the insulation that the cladding support is adjusted into. And so therefore your thermal benefits are mostly coming from that portion of the insulation that's left over that you've not adjusted into yet. And generally speaking, the thermal performance of these types of systems rely on really large, wide spacing of metal brackets rather than close, dense spacing. And that's because that, of course, the heat is moving through and thermally bridging through the metal brackets quickly, but if you space them apart far enough, there are few enough of them that the heat loss is further reduced, and we can achieve the necessary thermal resistance values that we need to meet today's codes. In comparison with that, a composite component can really be as dense as it needs to be. Some of them, like the thermal spacer there on the left, are strong and do not frequently need tight spacings. But you could, if you came to a part of a building that is just going to trigger tight spacings because of windows and corners and things like that, you could take a composite cladding support and make it more densely spaced without a thermal compromise or without a significant thermal compromise, because there's such little heat flowing through these composite components to begin with. But the composite components suffer from a different limitation. The main difference is the structural connection and the fire performance of that structural connection. With this example, using a thermal spacer, the connection of cladding on the outside to structure behind consists of a steel support connected by a single long steel screw all the way back to the steel stud. So we have this metal to metal to metal connection. And in most, all or nearly all composite cladding support systems on the market today, we don't often see that type of metal to metal to metal connection. That tensile connection of the cladding on the outside, therefore, is transferred to the fasteners through the combustible connection, which I'm sure if everybody's picturing that, they're thinking, okay, well, maybe that could work, but it would require a lot more fire testing. We know that a steel screw connected from inside all the way to outside is kind of safe by observation. So, best thermal performance from composite systems, but if there's no direct connection of fasteners, then fire safety is not obvious simply by observation. So that difference figured into the product design of that example that was on the left-hand side of the screen, that fiberglass Cascadia clip thermal spacer. So I want to lead you through a little manufacturer's story of how that product came to life in that form and how it addresses fire safety as part of the product design. So fire safety is critically important. That's actually where we have to start, and we have to stay with it and do all the other things around life safety. But why do anything at all? Well, we have a conductivity problem with the traditional single metal Z-girt, which does provide fire safety. Admittedly, that the single Z-girt's definitely safe in fire. If you make that Z-girt fiberglass, from a thermal efficiency perspective, you're done. It works. They're so low conductivity, these composites, that you're going to have about 3 times the efficiency of this layer of insulation, and you're definitely going to meet modern energy codes with moderate insulation thicknesses. But you end up with different practical problems. And here's how that went. So this was our first idea, just make a Z-gird into fiberglass. And then we realized, okay, screws are going to pull out of the outside leg when you try to attach cladding, unless you make this ridiculously thick. And so we're thinking fiberglass in this case, this very specifically calling it. In this particular case, I'm talking about fiberglass. So the solution here, we thought, okay, just outer leg, give better pull-out resistance by making it metal. Of course, this shape wouldn't stay together very well, but we'll resolve that in a second. The bigger issue right now with this design is to us, the combustible connection that exists. Cladding on the outside would be screwed to this metal on the outside. And then separately, a different fastener would be fastening to the structural wall. And the composite in between, the fiberglass in between, is combustible. And that would mean that your connection of cladding to non-combustible wall is a combustible connection. We thought it was a lot better and a lot more sleep at night factor to make that a non-combustible connection, which means move the fastening, make direct metal fastening from steel to steel to steel. Now, of course, this shape would rotate around the inner leg, but you can fix that by changing the shape. Remember, at this stage, this was not a part, it was a drawing of a part. So you can change it. Now, there's interference here between this web and this long fastener. So 2 webs provide a fastener path. That's looking like something you could actually build, but that's a pretty heavy, pretty expensive part now, this fiberglass section. And thermal performance could actually be better too, because there's so much solid material in that drawing. So if you chop it into pieces and you make it intermittent, you make something that's thermally a lot better because there's less fiberglass and more insulation itself. And it's also cheaper. It's also much more economically viable. But cutting it into pieces created its own separate problem. The new problem there is that installation becomes inconvenient unless there's a way to pre-assemble these pieces back into one stick so that one installer can handle the whole thing and connect it to a wall. So that's where this fiberglass shape gained this little retainer clip that grips onto the one continuous piece, the metal on the outside, and you can pre-assemble 3 or 4 of these onto a 1-story tall stick of metal and then attach it to a wall. And once you've got 1 screw in, the whole assembly is holding itself together. And now you need that continuous strip of metal to have some resistance, some stiffness in between these intermittent brackets. And so if you make it into a Z shape, you gain that stiffness and you gain a drainage cavity for your rain screen wall panels because you have some depth to that Z-girt shape. So that's where we got to when we said, okay, that's a product, that's a thermal spacer. And here then went us as a manufacturer's early experience of introducing what was an innovative product, that thing that you saw just sort of evolve slide by slide there, that became a product, and that needed to get out into the construction industry in a way that was safe from a code reviewer and a code compliance perspective. So we at Cascadia, that produces that space that I just led you through, we live and work in Metro Vancouver, British Columbia. So it was pretty natural for us to search for our first project in that area. And we found a project for that thermal spacer back in 2011 in Burnaby, which is a suburb in Metro Vancouver. And we proposed this spacer, and we actually retained a fire specialist, a building code consultant, to help us justify why we believe this complied with the building code. And what they said is that it is the same as other acceptable minor combustible components which the building code already permits. It doesn't explicitly name a fiberglass spacer, but it does explicitly explain that these minor combustible components are permitted. And that is actually a term, minor combustible component, in the Canadian building codes. So our code consultant says this is what it is, and the building official says, yes, we agree, but looking at this part, looking at the reason for it, improved energy efficiency in the future, don't you guys as a product supplier want an ability for this spacer to be more widely accepted and more easily demonstrate code compliance rather than having to hire a consultant for every project? And we said, well, yes, of course, this is one of our goals. And he says, well, why don't we then, instead of just having me accept your engineer's solution, why don't we send this for review by the highest code authority in British Columbia, which is the BC Building and Safety Standards branch, and they can review it and make their own decision and then publish that decision. And we did that. And the LMDG was our building code consultant. We actually had 2 building code consultants. The BC Building and Safety Standards branch reviewed this component, and they agreed, and they published a ruling that indicates that intermittent fiberglass spacers are, in fact, minor combustible components. It explicitly says it. So that Building Code Appeal Board's published ruling has been the simple method for code compliance really in all of Canada now. It's been widely adopted because the physics are the same coast to coast. And it was only when we wanted to enter the American market where, of course, the physics are the same even south of the 49th parallel, but the building code language is not. So, again, as a manufacturer trying to make the use of one of these innovative products easier for architects and plan reviewers working for municipalities, we had to go to a code evaluation agency, a well-recognized third party, because there is no such term in the International Building Code used in America as a minor combustible component. So even though that thermal spacer is a minor combustible component, that didn't matter in the United States. That wasn't a term. The existence of a list of permitted components that are combustible in a non-combustible construction does exist, and that is in Section 6 of the International Building Code, but it doesn't explicitly say fiberglass spacer, and it doesn't provide an umbrella term. So we went to this well-recognized code evaluation agency, IAPMO, and we asked their evaluation services department, can you review this component specifically, but not exclusively, for performance in fire, in non-combustible construction? And they said it's basically a washer. They looked at the existence of cladding support on the outside, steel cladding support, steel continuous screw, all the way back to steel stud. They said it's a different shape, but it's basically a washer. Well, that was a good start, but we still did a lot of performance testing to show that its existence wouldn't contribute in any way to a fire or a failure of a wall that has an expected fire performance from it. So one of the things that we put it through was an Nfpa285 test. So this is a real one. Previously you saw the computer illustrations of the Canadian version of this large-scale test, the S134. This is a real-life Nfpa285 test with a combustible ACM panel system, which passed, which did well. Everyone was happy at the end of this. It's a very aggressive test. And the idea was that use a combustible cladding because it's more aggressive. The combustible cladding might catch a thermal spacer on fire, and the thermal spacer might provide more fuel and contribute to the cladding spreading its fire, but no, that didn't happen. But the reason for selecting it was to select something that was the most aggressive situation. So we have this pass at the end of this test, and then we take it apart and we examine the parts. And the parts, the combustible parts, like the thermal spacer, that were right at that window opening, getting the full brunt of the fire for half an hour, were definitely charred because they're combustible materials, but they were still structurally intact. I stood on that. That's actually my hand holding that part. I took it, I stood on it, I shipped it back to our shop. It's still in one piece today. It's very interesting to note how much protection that mineral wool insulation, that non-combustible insulation, provides for exterior components behind it. You can see that combustible and relatively easily melted membrane is still intact, even just a couple of inches above that window. It's really well protected. You can even see the branding and the writing from the manufacturer on that membrane surface. So that mineral wool offered decent protection. Ultimately, what the code evaluation agency said about that thermal spacer component as a result of that testing is that for fire, the clip does nothing and therefore changes nothing. And what they meant by it doesn't change anything is that if an assembly with or without the clip has an expected level of fire performance, whether the clip is there or not, that expected level of fire performance will remain. It will not get better, it will not get worse. So the clip can go and do its thing from an energy perspective without changing the fire performance of the wall. And this particular agency published their certification of the Cascadia clip. It approves it for use in all types of construction under the IBC, types 1 through 5, which include the first two are non-combustible construction. And to our knowledge, it's the only component to this day that's recognized in a comprehensive third-party code compliance report like that, as far as a cladding support component that is a thermally improved component. The existence of helpful certifications took one step further. Intertek was retained by Rockwool Insulation to look at Nfpa285 assemblies which were done without exterior insulation. And now that we know that we need to use exterior insulation in some form on almost every construction, they wanted to see if there were cladding support assemblies with exterior insulation that could be introduced and still preserve the relevance of the cladding Nfpa285 test, even though that tested assembly did not include an exterior insulation layer. So what did Rockwool choose to test? Well, they chose to test a high density mineral wool insulation layer, which is illustrated on the left-hand side, penetrated only by fasteners. And then on the right, you see the medium density mineral wool with the fiberglass thermal spacer, again with the direct fasteners. So they tested both of those and they're successful. What this ruling now means is that, what this report now means is that in Intertek's evaluation, they're saying that if a cladding assembly with an existing Nfpa285 test was tested without exterior insulation, you can still use that test and have exterior insulation if you use one of these two assemblies. So I'm going to leave cladding now with a lens through which I would suggest that anybody on the call evaluates the fire safety by observation characteristics of cladding supports. And what you're looking for is non-combustible connections, in my opinion. So if you trace this detail, which has the exterior cladding on the bottom of the screen, and you trace, I'm just going to make sure that my pointer is actually visible to everyone. If you trace along that, that metal cladding support to the metal screw, continuous metal screw all the way to the metal stud, you could do that on a piece of paper without lifting your pen. And if you can do that without lifting your pen, you know that you have a metal to metal to metal connection and you have fire safety by observation. The fiberglass could become damaged in a fire. Whether it really does or not, it doesn't matter. It could become damaged and yet your cladding would stay attached to the building without a doubt. If, on the other hand, this cladding was attached to metal on the outside, but then there was just composite through to the inside and a separate fastener, that would mean that that composite is the only thing holding your cladding on in a fire. And that may be fine, but I haven't seen a lot of extensive testing on that point. Whereas if you see the direct metal connection, that's fire safe by observation. We just have to realize that we want as little metal as possible, because the more metal that makes that direct connection, the more thermal bridging comes and the less energy performance we get. So that's cladding, that's opaque walls. And I'm going to shift now to fenestration, which is the other half of our building enclosure, our building exteriors. Now, what are we specifically looking at in the building code when it comes to combustible fenestration? Well, first of all, combustible fenestration framing. Well, in Canada, unlike in America, America's kind of got this sorted already. They're like the rest of the world. They permit combustible windows. They realize that all windows are combustible. But we'll get there. We're not there for a few minutes. In Canada, we believe that only some windows are combustible and others are non-combustible. But the building code says you can use combustible windows. Combustible window sashes and frames are permitted in a building required to be of non-combustible construction, provided that. Then we have these three sentences, and two of them really play. we need a vertical 1 meter or 3'3" of non-combustible construction between windows on a story above compared to a story below. And we also need to have a limit of 40% of the area of a window, of the area of a building being combustible fenestration, not more than 40%. Before I go into the couple of problems with these rather antiquated limits, let's define what are combustible windows in terms of how the building code is practiced. So combustible windows consist of windows where their frames are made from fiberglass, other composites, or PVC or wood, which leaves non-combustible as an assumption for aluminum windows, even thermally broken aluminum windows. So whether the science backs that up or not, we'll get there in a minute. That is how the code is applied in Canada. So some of the problems that our code consultant brought up about this, these couple of obscure limits that exist in the Canadian building codes on the use of combustible windows is that to start with, why 40%? That seems kind of arbitrary. So the industry literally asked the Natural Resources Canada, NRCan, who regulates the building codes and implements code changes, why is the aggregate area of openings and exterior wall face of a fire compartment restricted to not more than 40% of the area as opposed to 50 or 60% or whatever? And they answered, based on our archived information, there is no available rationale behind the selection of 40% in the National Building Code. So it's arbitrary. Also, that 1 meter of vertical separation is relatively arbitrary in that it is so simply stated. On the right-hand side, this slide shows of 1 meter or 3'3" vertical separation from window to window. But on the left-hand side of that slide, the horizontal projection would actually provide greater protection to the story above if there was a fire in the story below. So even though the assumed intent of this 1 meter separation is to limit the vertical spread of fire, not recognizing a horizontal projection's helpful contribution is very odd if that truly is the intent, and the true intent of this is not explicitly stated. We still can assume that based on the overall intent and objectives of limits to combustible components, the overall objective is to limit, again, the severity and effects of fire and explosions. And if something doesn't align with the prescriptive requirements of the building code, there is always an opportunity to address it by alternate solution, which has actually been done in this instance for combustible windows used on non-combustible construction. But the industry took it a step further. So here's some background into a research project that resulted in a public building code change from a combination, a team up of private and public interests. So here goes. Again, the code issue is that while combustible windows are permitted, they are limited to, well, these two really play. And you saw this before. This is what it looks like on a building. 1 meter vertically here, not more than 40% glazing system. And I bet a couple of you have already looked at this photograph and gone, wait, the proportions on that photograph break both those rules, at least by a little bit. And you're right, if that's what you were thinking. This building is code compliant with these requirements through an alternate solution, not through the prescriptive solution that is the building code's sort of recipe-like language. Now, before we started studying how might these building code restrictions get changed, we wanted to do a bit of study internationally. Does this situation exist anywhere else? But no, it does not. Non-metal windows are commonly used in tall buildings due to their relative economy and better energy efficiency everywhere else. But Canada has a rather old building code, and despite the best efforts of people that update it, for example, when building sprinklers were made mandatory, indirectly affected aspects of the code do not always get an update. It's just simple simple fact that resources, including humans, are limited, can't do everything at once. Why is that clause itself so restricting? Well, classifying a window frame on whether it's just combustible is a problem because just saying whether it is or is not doesn't distinguish. Does it ignite readily? Does it promote the spread of fire or actually diminish it if you take away the source? Is it a lot of fuel or just a little bit? And it's restrictive because there's no other Western jurisdiction anywhere that classifies the fire performance of a window material on a criteria so narrow as Canada's code-referenced S114 test, which is a bench scale test that basically says, is something combustible or not in terms of how the building code treats it. So how about thermal breaks in these aluminum windows that are assumed to be non-combustible? Well, for decades now, building codes have wisely required thermal breaks in metal windows because they enhance energy efficiency. Even if it's just a little bit, every little bit counts. There is not one thermal break on this earth that is non-combustible. They're all combustible. None of them are capable of passing the code referenced S114 test. So on the basis of the code reference test, all windows in use today are combustible. Or you could at least say they have significant structural combustible components. So just think in your head, can you spot the code compliant window? And there's one of these three examples. And before I tell you which one, I'll describe the window frame materials that make them up from left to right. So moving through this window, plastic, metal, metal, middle window, metal, plastic, metal, right-hand side window, metal, plastic, metal, plastic, metal. But it happens to be the middle one. Why? I don't really know. I can't really tell you why it is that. Perhaps that company has marketed their windows as metal windows and the other ones composite or plastic, whatever the case is. But in the building codes perspective in Canada, the one in the middle could be used on 100% of a 40-story high-rise, and the ones on the left and the right would be limited to 40%. But from a scientific perspective, all these products are the same. So is this a real problem in the industry? Yes, we have more sophisticated products now than ever before. We need an evaluation criteria that keeps up. And the most energy efficient products in Canada and North America today are mostly or even wholly framed from PVC and fiberglass. So to not be able to use them for the majority of large scale buildings that need all the help they can get from an energy efficient products perspective, it actually diminishes the effectiveness of any energy code or any other energy conservation problem or program not to be able to use the most energy efficient products to get there. So we as an industry need to modernize the code. And the we in that sentence was the National Research Council of Canada and 10 window manufacturing companies across Canada that represented fiberglass, composite, PVC windows, and it added up to just a lot of fire testing, amongst which that large-scale S134 test was used as a demonstration of whole assembly performance. And I feel most comfortable showing photographs of our company's products. Therefore, I'm not making statements while showing somebody else's. But these were by no means the only products involved in the testing. But here's one example. So these are fiberglass windows, and the green line that I superimposed on this 3-story window assembly is that 5-meter limit. Flames may spread up to that green line, but not further. So this is a 1-hour test. The first half hour of it has, or first 25 minutes of it has fire. Fire starts in the fire chamber, ramps up for the first 5 minutes, and that's the fire at full bore after 5 minutes. And there's so much fuel used in this test that the fire actually comes out of the chamber, recruits new oxygen, continues to burn, and makes a big flame front coming up in front of the windows, which are essentially on the 1-story up from there. And like I said earlier, anything that's directly behind that flame front basically gets turned to ash. But that's okay. It's not necessarily going to compromise either of the two criteria to pass the test. So this was the maximum extent of burning at the end of the flaming periods, the end of the first 25 minutes, which was great because after that point, the window frame started to put themselves out on their own, and by the end of the test, put themselves out. So We were very happy about this. This is a fantastic demonstration of preserving fire safety. The glass in the second story windows didn't even break. So theoretically, any damage, even smoke damage, would have been very, very minimal on inboard in this assembly, just 2 stories up. But what was even more interesting is that we got to test aluminum windows as well. And after all that stuff I said about thermal breaks, we know that aluminum windows are combustible. And aluminum windows passed this test well. And on the basis of that, aluminum windows are safe. But fiberglass windows are also combustible, also pass that test, and therefore are also safe by extension of the same logic. So what can we do with this? Well, right now, this test result exists. And one of our code consultants, LMDG, that we've worked with the most, has indicated they're comfortable preparing alternate solutions now, and it's as simple as an engineering judgment now, up to and including that which was successfully tested. It's even easier these days than ever before to get this done because the building code is now changed on the basis of that successful research project. So the engineering solution or the engineering judgment to utilize both the reference to the tested product that was successful plus the upcoming change in the building code is a real simple 2-page letter with an attached test. And actually the window manufacturers that were involved in that testing, like Cascadia Windows, can help a potential designer through that and actually do it for them. So here's wrapping up here. Here's the timeline to the new normal for Canada's fenestration industry. Before all that research and testing, alternate solutions were always possible, but they had this give and take approach on shape and configuration and aspects of the building. Then that test happened, and we can look at that test, which was very aggressive, and say anything equal or safer than that test is obviously okay because we can see the results of the test. So alternate solutions became very standardized. Now that the code change is accepted for the upcoming 2020, which will be published later this year and adopted by the provinces after that, alternate solutions have just become a simple engineering judgment now. For examples of where alternate solutions have already been accepted include the City of Vancouver in British Columbia, a high number of them accepted there, West Vancouver, Hamilton, Ontario, and there's probably others in between. So it's getting simpler and simpler. And here's the change. This is the old text that is in the building code today. Combustible windows and sashes, sashes and frames are permitted in a building required to be non-combustible, provided that, and here's the new one, that they're vertically non-contiguous between stories. So if you look at an example product, actually that's directly it's big, but it's directly compliant with this statement, vertically non-contiguous. That means don't have combustible window frames outboard and bypassing your slab, like no plastic curtain wall. So that's not because it wouldn't necessarily be safe, that's just because that's beyond that which was tested. And this image in the bottom right of the slide shows Cascadia's relatively new fiberglass framed window wall, which is actually a hybrid between fiberglass framing that is on the inside and goes from the floor to the ceiling, and aluminum, which is the outer third of the product, which goes all the way floor to ceiling as well, plus it extends in front of the concrete slab and makes the slab bypass, as is typical in a window wall. The reason why this fiberglass framing that goes floor to ceiling is compliant with this code, with this requirement that it is not vertically contiguous between stories, is that the only components that are vertically contiguous are not combustible. They include metal, glass, and mineral wool. So this is the end of the technical part of the learning session. This is everybody that's made it this far with me. Thank you very much. You're receiving your learning credit. I invite your questions. Please go ahead and ask me any questions. While you're thinking of them and writing them, I'm going to spend the last 60 seconds or so just summarizing what products that you might count on Cascadia Windows for if this has opened your eyes to the opportunity to incorporate more of these types of products into your building for extra energy efficiency. So what do we make? We make fiberglass punched windows and doors, and an option that they are Passive House certified, if that's needed. And fiberglass strip windows, also an option that they are Passive House certified. Fiberglass storefront windows, and the interesting part here is, yes, you can use them for storefront. They're way more thermally efficient than what you'd use. They perform like curtain wall in terms of air tightness and water penetration resistance, but they're far less costly than curtain wall, and they're factory finished. So they come as factory built units that just need to get fastened and sealed to the building, and then the installation's done, as opposed to being stick built on site. We offer as an option storefront doors, fiberglass storefront doors as well with the storefront system. They don't have to take fiberglass doors. You can use the metal doors that might be already commonly in your spec. You can integrate the doors by others into the fiberglass framing if you choose. Window wall. Cascadia last year launched the world's very first fiberglass window wall with the intent of bringing the energy efficient yet structurally predictable and long life characteristics of fiberglass windows to commercial and high-rise construction. So if you have a project where you need a window wall with a slab bypass, you can now have a fiberglass window wall performing that function. And of course, the last but not least, the fiberglass thermal spacer known as the Cascadia clip, which you saw in many of the earlier slides when we were talking about opaque walls. If you have an opaque wall and you have an exterior insulated cladding support system, this Cascadia clip will combine the structural efficiency and the energy efficiency to actually make possible the lowest dollars per R value wall that you can build in terms of the cladding support assembly. So thank you everyone again for sticking with us through that whole learning session. And for participating in our audience interaction slides. Feel free to ask your questions, and if I don't get any questions, or if I get through the questions and there's no questions for 10 or 20 seconds, and we're going to call it a day. All right, and any of my colleagues that happen to have joined, whether I noticed you or not, you're also welcome to remind me if any of your contacts have asked you questions along the lines of this subject matter, which have come up more than once or twice, and I'm happy to address those for the good of the group as well. Sometimes people ask me, when is the building code going to change to make this simpler? And well, so the answer is that the 2020 building code is written now. It's going to be published later in 2020, but it commonly takes a year, even a bit more, for the provinces to get to their own code cycle where they adopt the new 2020 NBC into the provincial level. So for Canada to use and to gain the advantage of this code change, we still need to do a simple engineering judgment, but on a project by project basis for at least the next year to year and a bit. Couple of questions here. Any idea on fiberglass clip price? Yeah. Well, so since that product is our product, I'm happy to comment on that. A couple of ways that I can express the price. You know, a 4-inch deep clip is about $4, give or take. So that doesn't tell you a lot about the cost of the whole wall, because that information doesn't tell you how far apart the clips are spaced. To determine how far apart the clips are spaced, you can actually go onto the CascadiaWindows.com website and go to one of the tools called a Cascadia Clip Calculator. This calculator enables any user, architect or cladding contractor or anybody, to enter some simple inputs like steel stud or other backup wall, the weight of the cladding that's going to go onto the clips, and then play with a couple of spacings. For example, 16 by 48-inch spacing would require fewer clips than 16 by 24. And so you play with these spacings and you review the output of the calculator. The output of the calculator includes the thermal resistance of the whole wall and the allowable wind load of the whole wall, while it is already taking into account the weight of the cladding. And so in this way, with a bit of trial and error, you can determine the widest and therefore most economically efficient spacing of the Cascadia clip system. When you do, for sizes in the smaller end of the range, which are, I would say, 2.5, 3-inch sizes, and that's equal to the insulation thickness, those Cascadia clips plus the fasteners plus the metal cladding supports on the outside as a collection of 3 parts, that'll usually run $2 to $3 a square foot for the wall, if the spacing's optimized, and if that gets expanded to kind of the bigger end of the range, 5, 6, 8 inches, that's probably going to add about another $1 per square foot or so. So $2 to $4 per square foot for those components from the material costs. Hope that's useful for the person who asked about price. If there are any other questions, please feel free to present them. One of the questions came in, does Cascadia have any single-family residential home windows, or are the fiberglass windows mainly for high-rise or commercial buildings? So thank you for that question. We do happily have quite a number of single-family homes which have used our windows, and we continue to serve that type of business. The examples of the custom homes that have incorporated fiberglass windows, they're all shapes and sizes. There's usually something special that the owner of the building is looking to capture, like in the case of this example, the view in Squamish. Usually something special that is sought. The general combination of characteristics that a single-family homeowner gains from selecting fiberglass windows is they're getting a commercial grade yet very energy efficient product, which is an unusual combination of characteristics. So they're able to have way bigger windows than vinyl, way more energy efficient windows than aluminum, and very, very long life windows that don't require a lot of maintenance over many, many decades of service life. So if that's interesting to a single family home client, or you are the client or a builder, so I hope that's useful there. Another question, might it be possible to have a window wall in the exterior wall of an exit stair that is continuous without the small spandrel sections? Of course, since there's no story within the stair. It's a very interesting question, but I don't think I'm able to answer it exactly for 2 reasons. Number one, I don't have enough code expertise to comment on that. Another thing that I'm familiar with is that in a public building, exit stairs, if the exit stair is on the outside of the building, on the outside of the building enclosure, that wall usually has to be a rated wall, not just a non-combustible or a tested assembly, but literally a firewall to preserve the possible use of that stair even in a fire. But if the stair is fully inside of a firewall that's surrounding it, and then you're just asking, could the outside surface of that firewall that encloses the interior stair, could the outside surface have fiberglass windows down it? I think in some cases, yes. But if you have a specific example of that, feel free to contact us, and we can actually recruit a little bit of advice from our fire code consultants to supplement our own internal technical support that we can offer to any client. So really interesting question there. Thank you for submitting that. Sorry I can't answer it definitively, but if you'd like to contact me afterwards and continue that line of conversation, I welcome you to do it. Okay, so everyone, we're a few minutes over. Thank you for sticking with us during the question period. I'm going to stay on the line for about 10 or 15 seconds to check if any other questions come in. If not, thank you all once again. If you have any interest in contacting us to follow up, please simply reply to the email that you received from the webinar system, or look us up by going to our webpage in the Contact Us area and finding the contact that's closest to you. All right, so I think that's the end of all the questions. If you were furiously typing and I'm going to cut you off before you submit your question, I apologize, but then just please submit it to me by email and happy to help. Thank you, everyone. Have a great day.